Okay. Yeah, I'll start with the introduction and then hand it off to you. So hello, everyone. Welcome to the final quantum engineering graduate seminar. Today, it's my great pleasure to introduce Dr. Riccardo Manenti. Dr. Manenti is a senior quantum engineer working at Rigetti Computing. He earned his PhD in superconducting devices at Oxford. His project helped create a new subfield of condensed matter physics known as circuit quantum acoustodynamics. His work at Rigetti currently focuses on the design of superconducting qubits and the calibration of two-qubit gates using pulse shaping. A little bit about his recognition. In 2019, he received an award as the best Italian physicist under 30 in the US. The same year, he was included in Forbes 30 under 30. I guess you're the second Forbes 30 under 30 speaker we have. Dr. Manenti is currently writing a book for Oxford Press entitled Quantum Information Science, which is going to be published next year. In today's talk, he'll be explaining the physics of superconducting devices and present the major challenges in scaling a quantum computer based on these Josephson junctions. So that was a very brief introduction. And with that, I'll pass it on to Riccardo. Thank you.
Thanks a lot. Thanks a lot for your introduction. So in this talk, I would like to explain the physics of superconducting devices. I joined Rigetti 5 years ago as a quantum engineer, and I work on the calibration of the two-qubit gates as well as on the design of the devices. So my presentation is divided into 5 parts. At the beginning, I will talk about a little bit about our company. Then I will address the question, why are we building quantum computers? At that point, I will dive into the physics of superconducting devices and explain some of the challenges in scaling these devices. And then finally, I will answer to any question. So Rigetti Computing was founded in 2013 by Chad Rigetti. The company has 2 sites, one in Berkeley and one in Fremont, and also has a new site in the UK, where we also have some dilution refrigerators and a quantum computer connected to the cloud. So the actual fabrication of the devices are performed in Fremont. The main lab with most of the dilution refrigerators is in Berkeley in California. These 2 sites are only 1 hour away from each other. This is an image of the lab in Berkeley. Here you can see 4 dilution refrigerators. And this is an image of our fab facility in Fremont, where we fabricate the actual devices. Here, this facility is dedicated entirely to the fabrication of superconducting devices. So let me move on to the next part of the presentation, in which I try to answer the question very briefly on why are we building quantum computers. So first of all, as you know, in complexity theory, there are many classes. Probably the most important one is the class P, which contains the decision problems that can be solved by a deterministic Turing machine in polynomial time. This class roughly corresponds to the problems that can be efficiently solved by a classical computer. There is another important class which is called NP, which contains the decision problems whose affirmative solution can be verified by a deterministic Turing machine in polynomial time. So problems in P are like multiplication, addition, very simple mathematical problems. An example of problem in NP is, for example, the RSA problem. Given an integer, there is a product of 2 semi-primes. We want to find these there is a product of 2 primes. We want to find these prime numbers. So this problem is very difficult for a classical computer, but can be solved in polynomial time by a quantum computer. And then we have like the class of problems NPC or NP complete problems. These are problems that are inside the class NP, and then all other problems in the class NP can be reduced to these NP complete problems. An example of an NP complete problem is, for example, the traveling salesman problem, or for example, 3SAT. So BQP is a quantum complexity class. In this class contains all of the problems that a quantum computer can solve in polynomial time and a small error probability. So something that I should stress is that right now there is no rigorous proof that P is different from NP. This is like the $1 billion question in complexity theory. And so we cannot even say what the relation between P and BQP is. However, many scientists working in complexity theory believe that this is the current situation for complexity classes, because after years and years of attempts, nobody has ever managed to show a classical algorithm running on a deterministic Turing machine that can solve an NP complete problem in polynomial time. So an interesting thing is that some problems very important to the physics community, such as the simulation of the time evolution generated by Hamiltonian. So the problem of the Hamiltonian dynamics is in BQP. So some quantum algorithms that can solve this problem are, for example, the characterization, the qubitization. So these are different techniques to study the time evolution of a quantum system in polynomial time with a quantum computer. And this is the original idea by Feynman when he proposed using a quantum computer to study the dynamics of a quantum system back in the 80s. Okay, so to build a quantum computer, we need to satisfy some criteria. These criteria are also known as De Vincenzo criteria. So first of all, we need a physical system with well-characterized qubits. We also need the ability to initialize these qubits in a specific state, such as 000 and so on. Then we need qubits with good coherence times. So the coherence times should be much longer than the typical gate time. And then we must be able to measure the qubits. And finally, we must be able to run a universal set of quantum gates. So for example, single qubit rotations and the C0 gate or the I swap gate. So how do we build quantum computers at Rigetti? So first of all, we use the superconducting qubits as the physical system. We cool down the qubits at very low temperature, around 10 millikelvin. So the initialization of the qubits in the state 0 is pretty simple. Then to improve the coherence times, this requires a lot of materials science. So engineering the interfaces between the superconducting layer and vacuum, between the superconducting layer and the substrate, and so on. For measuring the qubits, we use dispersive coupling with microresonators. With a microresonator, which is at the core of circuit quantum electrodynamics. And finally, to run 2 qubit gates, we use parametric gates as well as fast DC gates. I will talk about these, about 2 qubit gates at the end of the presentation. So let's move on to the physics of superconducting devices. So I will start by explaining the transmon, and then I will talk about the properties of a transmon and how to operate single and 2 qubit gates. So the transmon can be imagined as 2 pieces of metal, so 2 pieces of aluminum or niobium. So the metal must be superconducting. So connected by a junction, a Josephson junction. The area of a junction is approximately 200 by 200 nanometers. And the size of a qubit is approximately 1 millimeter. The substrate typically is either silicon or sapphire. And then the metallic layer is either made of niobium, titanium, or aluminum. The thickness of the superconducting layer is around 100 nanometers. And this oxide barrier between these two aluminum layers is approximately 1 nanometer thick. And the superconducting qubits are usually fabricated with standard photolithographic techniques. This is an image of an actual Josephson junction. As I mentioned before, the overlapping area is around 200 by 200 nanometers squared. This image was taken with an electron microscope. The two pods can be designed with different geometries. This is probably the simplest design that you can think of. It's it's a very simple transmon, two pods connected by a Josephson junction. But back in 2008, 2010, this was another popular design, but then it was abandoned because it was not really good for the coherence time of a qubit. The participation ratio was not it was not good. This was a geometry that was using during my PhD at Oxford, is still used by that group. And then finally, this geometry that is used by many groups now, like, for example, the Google group, but also the MIT group has used this type of transmon. Since this transmon looks like an X, sometimes it's also called an Xmon. So one question could be, why are superconducting qubits so big? If you think about transistors are 50 nanometers big, so they're really, really small compared to standard superconducting qubit. A superconducting qubit is around 1 millimeter in size. So one natural question would be, is it possible to decrease the size of the capacitor? So if we decrease the size of a capacitor, we end up with a Cooper pair box. I will explain this in a second. So if we build a superconducting qubit with a much smaller capacitor, then we would not be in the transmon regime anymore. We would be in the Cooper pair box regime. And unfortunately, the phasing time of a Cooper pair box is not does not exceed 1 microsecond. So let's now try to understand the Hamiltonian of a Cooper pair box and the one of a transmon. So we can start by looking at the electrical circuit for a Cooper pair box. We simply have a capacitor and a Josephson junction in parallel. And this system is characterized by two energies, the Josephson energy and the charging energy. So the charging energy can be adjusted by changing the size of a capacitor, while the Josephson energy can be adjusted by changing the resistance of a junction. Indeed, the critical current is related to the resistance of a junction by the Ambegaukar-Baratov formula. So, for example, if we build a superconducting qubit, we measure the resistance of the qubit, and we notice that is not around 5 or 10 kilo ohm, but for example, is like 10 mega ohm, then we know for sure that that qubit is not working. So that's like an easy way to understand if a qubit is gonna work or not once we cool down the fridge. This can simply be done by measuring the resistance of a junction at room temperature. The Hamiltonian of a Cooper pair box is very similar to the Hamiltonian of an LC resonator. So for an LC resonator, we have two contributions, and the Hamiltonian resembles the one of a quantum harmonic oscillator. Here, the operator n corresponds to the momentum of the particle. The operator phi corresponds to the position of the quantum harmonic oscillator. The Hamiltonian of a Cooper pair box is very similar. The only difference is that the inductor has been replaced by the Josephson junction. And instead of having this quadratic term on the right, we have a cosine term. So now that we have the Hamiltonian, we can also consider how the Hamiltonian is going to change if we connect a voltage source to the circuit. So if we connect, for example, a battery to this circuit with a capacitor, a gate capacitor, the Hamiltonian is going to change in this way. So this term appears. This Ng is a continuous quantity that is related to the voltage applied by the voltage source. So this is a continuous quantity that can be varied by the experimenter. Okay, so now that we have the Hamiltonian, we can find the energy levels of a Kuiper pair box by solving the time-independent Schrödinger equation. So this differential equation doesn't look very simple, but actually it's possible to solve it analytically. And the energy levels can be expressed in terms of, Matthew functions. So now we can plot the energy levels as a function of the gate charge, Ng, which, as I said before, is related to the voltage applied by the voltage source. And this is what we obtain. So these are the energy levels of a Kuiper pair box as a function of the gate charge. So the charge accumulated on this capacitor. As you can see, the energy levels are periodic, and then as you can see, they strongly depend on the gate charge. So there are many energy levels, but we're only interested in the first two, and we can use the first two energy levels to form a qubit. So we are going to use these two levels as a qubit. The problem with a Kuiper pair box is that the dephasing time is very small. To understand why, we should remember the fact that the dephasing time is inversely proportional to the qubit frequency. So the qubit frequency here is around 4 gigahertz. The qubit frequency here is around 16 gigahertz. So since the dephasing time is inversely proportional to the derivative of the qubit frequency as a function of a specific parameter, it makes sense to bias the Kuiper pair box around this point where the first derivative is equal to 0. However, the second derivative is not equal to 0. And for this reason, if you consider like typical quantities for these variables, you soon discover that the dephasing time of a Kuiper pair box is limited to 1 microsecond. So in 2007, the Yale group introduced the transmon, which is a Kuiper pair box working in a different regime, where the ratio between EJ and EC is not equal to 1, but is much bigger. So for example, if it's equal to 55, this is how the energy levels look like. They're flat, they're almost flat. And the dephasing time, due to charge noise, due to the fact that the voltage source might not be stable. And so that means that the charge accumulated on this capacitor can change a bit. So the dephasing time due to charge noise is bounded to 20 milliseconds. So this does not mean that a transmon has a dephasing time of 20 milliseconds, because the dephasing time is given by several different contributions. So one of them is a charge noise, but there are like many other contributions like flux noise and so on. So at least the charge noise is not the limiting factor anymore. The typical dephasing time for a transmon is between 1 and 100 microseconds. So in this slide, I show you the potential for the harmonic oscillator and the potential for a transmon. As I mentioned before, the main difference is that here we have a quadratic term, here we have a cosine. So that means that the potential is slightly anharmonic, and the transition frequencies between 0 and 1, 1 and 2, and 2 and 3, they're all different. So that means that if we send an electrical pulse to a transmon, we can excite the transmon from 0 to 1 without exciting the system also to 2, 3, 4, and so on. Instead, when we have a quantum harmonic oscillator, for example, a micro resonator connected to voltage source, and we apply an electrical pulse, then the system goes into a coherent state because these levels are equally spaced. By studying this Hamiltonian, one can find the energy levels of a transmon. They depend on EJ and EC, and also the frequency of a transmon, which is given by this formula. And then finally, the anharmonicity, which is an important parameter. This parameter is basically the difference between the transition frequency between 1 and 2 and the transition frequency between 0 and 1. For a transmon, the anharmonicity is negative. So the typical value of the anharmonicity for a transmon is between -200 and -300 megahertz. Okay, so one thing that I would like to mention is that these devices are cooled down to 10 millikelvin. And the reason is that the typical frequency of a transmon is around 4 or 5 gigahertz. The reason is that all our commercial electronics has been developed at these frequencies. So it makes sense to have our superconducting qubits at this frequency. And if we cool down the device at 10 millikelvin, so T is equal to 10 millikelvin, then the thermal radiation is not energetic enough to excite the qubit from 0 to 1, because, I mean, with a basic calculation, you can see that the energy of photons emitted by the black body radiation surrounding the device is around 200 megahertz. Clearly, if the temperature of a fridge increases, then the state of a qubit would become a thermal state. The transmon that I showed you in these slides is a fixed frequency transmon. This transmon has only a capacitor and a Josephson junction, but to make it tunable, we can add an extra Josephson junction so that we form a squid. By applying a magnetic field through a squid, we can change the qubit frequency. So this is very useful, especially to implement 2 qubit gates. If the 2 junctions have the same size, this is how the qubit frequency looks like as a function of the magnetic flux threading the squid. If instead the 2 junctions are asymmetric, so one is much bigger than the other, the frequency of a qubit moves, for example, from 5 gigahertz down to 3.5 gigahertz. And we have like a maximum and a minimum, which in this plot are called F max and F min. One thing that I should mention is that the typical size of a squid is around 20 by 20 micron. Here you can see an actual image of a tunable transmon. You can see the 2 pieces of metal. So that's niobium, that's another piece of niobium, and they're connected by a squid that you can see here. And this is a zoom in. As I mentioned before, the typical size of a squid is 20 by 20 micron. And then on the left, you also see the Z line. So this is a flux bias line that we use to deliver current to the qubit. The current flows in this direction, and then it creates a magnetic field that threads the squid. And in that way, we can change the qubit frequency. So this is like the qubit frequency as a function of flux. And then something that we could do is to measure the dephasing time of a qubit at each point. And clearly the dephasing time is high, close to this flux insensitive point. And then the dephasing time decreases as we move away from this insensitive point. Let's talk about how to drive a transmon. So to drive a transmon, we can simply connect the transmon to an XY line. So this is a waveguide that is connected to a voltage source outside the fridge. If we apply an electrical pulse down this line, we can implement single qubit rotations. So the Hamiltonian of this system is given by this equation where V dt is the actual electrical pulse applied by the source. The typical electrical pulse has a Gaussian shape that I'm showing in this diagram. And in this way, we can implement rotations in the Bloch sphere. So we can move the qubit from 0 to a superposition state. So this Gaussian pulse has a modulation that is described by this quantity epsilon t. So this is the modulation. And then by a frequency that is indicated by this parameter omega d, and then a phase, which is alpha. So if we want to excite the QB from 0 to 1, then we need to apply an electrical pulse with a frequency omega d that is pretty close to the actual QB frequency. So in that way, we can move a QB from 0 to 1 or from 0 to a superposition state. The phase of a pulse is quite important, because if phase is equal to 0, that that implements rotation about, for example, the y-axis. If alpha is set to pi over 2, then the rotations take place around the x-axis. So by changing the phase of a pulse, we can perform a single QB rotation about a particular axis lying on the equator of a Bloch sphere. Here, A is simply the amplitude of a pulse, and in this case is normalized to 1. So to calibrate single qubit gates, we can run, for example, a time-Rabi experiment. In this experiment, we send an electrical pulse to the qubit, and then we measure the state of a qubit. So in this experiment, we are simply changing the gate duration, and then we measure the probability of finding the qubit in the excited state. As you can see, the probability has this sign behavior, and in this specific example, pulse is 25 nanoseconds long, implements a pi half pulse, and a pulse is around 50 nanoseconds long, implements a pi pulse. When we calibrate single qubit gates, it's much easier to, makes much more sense to fix the gate time and change the amplitude of the pulse. So this is what we call the power-Rabi experiment. So the time is fixed, the pulse duration is fixed to 50 nanoseconds, for example, and then we change the amplitude of the electrical pulse. So again, the probability oscillates like a sine, and we have, in that way, we can calibrate the amplitude required to implement a pi pulse, and the amplitude required to implement a pi over 2 pulse. So something that is really important is that any single qubit gate can be decomposed in this way. So that in this decomposition, you can see that there are like rotations about the z-axis and rotations about the x-axis. So the z rotations can be implemented in a virtual way. I'm not gonna go into the details of this, but the idea is that we don't need to actually send a physical electrical pulse to implement a z rotation. That is something that we can do in software. Instead, the pi half rotation is the only gateway that we really need to calibrate. We can calibrate this gate really well, and in that way we can then implement any single qubit gate. One thing that is important to mention is the fact that transmons are not two-level systems. They also have a second excited state, third excited state, and so on. And for that reason, if the pulse, we simply use a Gaussian pulse, the trajectory on the Bloch sphere can be distorted, especially when the electrical pulse is very short. So we're talking about like 5, 10, or 20 nanoseconds long. So if it's very short and the anharmonicity of a QB is very small, then this can cause some problems. So to overcome this limitation, we can implement a technique known as the drag technique, in which we not only send a Gaussian pulse on one quadrature, but we also send the derivative of a Gaussian on the second quadrature. In that way, we can reduce phase errors and leakage to the second level. Let's talk about measuring a transmon. So to measure a transmon, we simply connect the qubit to a microresonator, and this is really at the core of circular quantum electrodynamics. So let's start from a simple measurement, the measurement of a microresonator. Here you can see a coplanar waveguide resonator connected to a waveguide. So we have a signal traveling from a left to a right, and the coplanar waveguide, in this specific example, we have a λ/4 coplanar waveguide resonator, is capacitively connected to the waveguide. Here you can see that there is like an open, and then on the other side we have a short. Coplanar waveguide resonator, the typical length is between 4 and 5 millimeters. When we measure the coplanar waveguide resonator, we see a resonance. So here I'm plotting the transmission coefficient, which is the ratio between the output voltage and the input voltage. So here I'm plotting the magnitude. And you can see that in this example, we have a resonance at 7 gigahertz. The width of the resonance can give us important information about the quality factor of the resonator, so the performance of the resonator. So now what happens if we connect the resonator to a superconducting qubit? So if we connect the resonator to a qubit, then the transmission coefficient depends on the state of a qubit. So this is the Hamiltonian of the system, in which we have the Hamiltonian for the microwave resonator, the Hamiltonian of the qubit, and then a term that describes the coupling between the qubit and the resonator. So this is also known as the Jaynes-Cummings Hamiltonian. When we work in the dispersive regime, so when the qubit frequency is, and the difference between the qubit frequency and the frequency of the resonator, which is called the detuning. When the detuning between these two systems is much greater than the coupling strength G, then the Hamiltonian can be written in this way. So this is like a first order approximation, in which we have a term that describes the resonator, another term that describes the qubit. You can see that the frequency of the resonator depends on the state of the qubit. So this is really the most important point about circuit quantum electrodynamics. This is a state-dependent transmission of the resonator. So we send a signal down this line. If a qubit is in the ground state, we're going to see a resonance of 7 gigahertz. If a qubit is in the excited state, the resonance shifts to the left by a quantity that is 2 chi. Chi is the dispersive shift, which is determined by the coupling strength and the detuning between the qubit and the resonator. So in this way, we can tell if a qubit is either in the ground state or the excited state. We simply need to measure the transmission coefficient through this waveguide. The coupling strength G can be adjusted by changing the capacitance between the resonator and the qubit. And here you can also see the XY line and the Z line that we need to implement single qubit rotations and change the qubit frequency. When we measure a qubit in a superposition state, for example, if we do this experiment 1,000 times, we approximately, we're going to find the qubit 500 times in 1 and 500 times in 0. So in this plot, I'm plotting the real and imaginary part of the signal coming out from the waveguide. So if we now project these two blobs, we are going to see two Gaussians. And the signal to noise ratio can be defined as the ratio between the distance between these two Gaussians and their width. So a good signal to noise ratio is achieved when these two Gaussians are really well separated. To increase the signal to noise ratio, one could also employ Josephson parametric amplifiers on the readout line to improve the readout fidelity. Once so with this technique, we can measure the energy levels of a transmon by doing, for example, qubit spectroscopy. This is a pulse experiment in which we send first a pulse to the qubit and then a pulse to the resonator. We change the frequency of the pulse from, let's say, 3 and 4.1 gigahertz. And then we constantly monitor the transmission coefficient of a resonator. If a transmission coefficient of a resonator changes, that means that we have excited the qubit. So this is a typical qubit spectroscopy in which we see the resonance of a qubit, F01, and then we also see resonance on the left. And this is like an excitation of a second excited state with a two-photon process. The width of this Lorentzian can give us some information about the dephasing time of a qubit when the experiment is performed at low power. However, T2 can also be measured in a much more accurate way by running a Rams experiment. Let's move on and let's talk about two qubit gates. So if single qubit gates can be performed with fidelities of 99.9% pretty easily, two qubit gates are much more challenging. So in this slide, you see two qubits connected together by a capacitor. So this is not an actual image of a device, is just a schematic to have an idea of how the device will look like. We have two transmons, they are capacitively connected to each other, and we have an XY line on the left, one on the right to implement single qubit rotations, and then a Z line for each qubit to change the frequency of a transmon. So the Hamiltonian for these two qubits is given by these three terms: the Hamiltonian of qubit 1, the Hamiltonian of qubit 2, and then the coupling term. So in this case, I'm approximating the qubits as two-level systems, but clearly one will also need to include higher energy levels. The coupling strength between the two qubits is mainly determined by the capacitor C12, the capacitor connecting the two qubits. So in this diagram, it would be the capacitance between these two pads. So this is not the only way to connect two qubits. Another popular way of connecting two superconducting qubits is by using a bus coupler. So in this case, a coplanar waveguide. So we have, these can be useful, especially when we want to space the qubits at least 2 or 3 millimeters apart, so that we can introduce other elements in the circuit. The only thing that changes is that these the coupling strength now depends on G1 and G2, the coupling between each qubit and the resonator, and then the detuning between the qubits and the resonator, delta 1 and delta 2. So if we want to activate a two qubit gate, we can run, for example, an I-swap gate. The only thing that we need to, this is probably the simplest two qubit gate. We just need to change the qubit frequency of qubit 1 such that the qubit frequency overlaps with the frequency of a neighboring qubit. So for example, the qubit starts at 5 gigahertz, we apply a flux pulse, the qubit moves to 4 gigahertz, and then we bring it back. As it's shown in this diagram on the top right. We apply a flux pulse, the two qubits get into resonance, and then qubit 1 goes back to Fmax. So if we study the time evolution operator of the Hamiltonian that I showed you in the previous slide, this is what we obtain. And then if the gate time is the duration of the flux pulse is exactly pi over 2g, then this flux pulse implements an I-swap gate with an extra minus sign. So this is an actual experiment where you can see the energy transfer between one qubit and the other qubit. This experiment is sometimes called a swap spectroscopy. We apply a pi pulse to one qubit, then we apply a flux pulse to the same qubit, and then we vary the pulse duration. And you can see the energy transfer between one qubit and the other is a periodic in time. And you can see that when one qubit is in the excited state, the other qubit is in the ground state. So in this specific example, an I-swap gate can be implemented in around 40 nanoseconds. There are like different ways to implement two qubit gates. This is the one that I showed you in the previous slide, in which we apply a flux pulse to one qubit. Another way to implement a two qubit gate is by applying an RF pulse. So now the flux pulse is not a DC pulse, but oscillates in time. So that means that the qubit frequency oscillates around Fmax. And if the average qubit frequency overlaps with the frequency of a neighboring qubit, then that implements an ISWAP gate. We can also implement CZ gates, for example. Again, we can send a flux pulse to the qubit, and now the qubit frequency moves, but it does not exactly overlap with the frequency of a neighboring qubit, but there is like detuning that is equal to the anharmonicity. So that implements a CZ gate. We can also, instead of sending a simple DC fast flux pulse, we can also send a bipolar pulse. This was a study by the Riccardo group in 2019, and they noticed that this improves memory effects. And then finally, we can also send a parametric pulse to implement a 2-qubit gate. So one limitation of these schemes is that when the 2 qubits are connected to each other, there is always a coupling. There is always a finite coupling between them. So we have the 2 qubits that are connected by a capacitor, and the problem is that there is always a finite coupling between the 2 qubits. You can see this by analyzing the Hamiltonian of the system in the dispersive regime. And you can see that the frequency of qubit 2 depends on the state of qubit 1. So this is quite problematic if ZZ coupling, so this is a coupling strength, is too high. It's a problem because if you think about it, if this qubit is excited, the frequency of a neighboring qubit changes, and that is problematic for simultaneous single qubit gates. Because if I run a single qubit gate on this qubit, then the frequency of this qubit moves. And that means that if I try to implement a high fidelity single qubit gate on this qubit, it's going to be challenging because there are going to be phase errors. The qubit frequency has moved. So the ZZ coupling can be measured with a Ramsey type experiment like this one. So this is the challenge. On one end, we would like to have a strong coupling between the 2 qubits so that the 2-qubit gate is the 2-qubit gate time is short. But on the other hand, if a ZZ coupling is too strong, the fidelity of simultaneous 2-qubit gates is low. So how do we solve this problem? So the one proposal was to use tunable couplers. So the idea is to insert an extra qubit between the 2 qubits. So a tunable coupler is nothing but an extra superconducting qubit, so an extra transmon, for example, connecting these 2 transmons. So the important point is that in the first proposal, the important point was that there was a direct capacitance between the 2 qubits, and also this strong coupling between the qubit and the tunable coupler and the second qubit and the tunable coupler. So the most important point here is that the coupling strength between the 2 qubits now depends on the frequency of the tunable coupler. So by choosing the in an appropriate way the frequency of a tunable coupler, we can set the effective coupling between the 2 qubits to 0. So this is the important point. If we want to run high fidelity single qubit gates, we can bias the coupler at a point where the coupling is set to 0. So we can run high fidelity single qubit gates. And then when we want to run a 2-qubit gate, we move the coupler frequency so that the coupling strength between the 2 qubits increases. And then at that point, we implement our 2-qubit gate. So we discovered in 2021 that the geometry of the tunable coupler is really important. It can be either symmetric or asymmetric. And depending on the shape and the design of the tunable coupler, the G equal to 0 condition, so this condition that I showed you before, happens either when the tunable coupler is below the qubit frequency or above the qubit frequency. So we tested these hypotheses by studying for the capacitance network. This is quite involved. You can find the information in this paper that we published last year, but also experimentally by measuring the coupling strength as a function of the tunable coupler frequency. As you can see, the qubits are parked around 4.8 gigahertz, and the G equal to 0 condition is achieved when the coupler frequency is below the qubit frequency. Instead, for this geometry of a tunable coupler, so for the asymmetric design, the G equal to 0 condition is achieved when the coupler frequency is above the qubit frequency. Okay, now that we have a tunable coupler, we can implement an ISWAP gate or a CZ gate with similar techniques to the ones I showed you before. And we can, for example, benchmark our gates with a quantum process tomography. And then we can also run randomized benchmarking to test to measure the fidelity of our 2-qubit gate. We've measured the fidelity on a device with 9 qubits, and we were achieving on all edges 99% fidelity. And these measurements were quite stable over the course of a few hours. So the last part of the presentation will be about the challenges in scaling these devices. So one of the problems of superconducting devices, one of the challenges I would say, is how to scale these devices to thousands and thousands of qubits. So first of all, one thing that we must consider is the number of lines that we need to operate these devices. So the number of lines depends on the 2-qubit gate scheme that is used. So if we have all of the qubits that are like flux tunable, we need an XY line per qubit and a Z line per qubit, so 2 lines per qubit. If we use an all microwave approach, we don't need Z lines, we just need XY lines, so just 1 line per qubit. So for example, if we run the cross-resonance gate, then we will not need more than 1 line per qubit. Instead, if we use also tunable couplers, then not only we need 2 lines per qubit, but we also need a Z line per tunable coupler. So the scaling is a bit worse if we employ tunable couplers, but there are also other challenges for these approaches. So for example, the cross-resonance gate tends to be slower compared to 2-qubit gates based on tunable couplers. And on top of that, the cross-resonance gate imposes stringent requirements on the qubit frequencies. So the fabrication must be very accurate. So to reduce the number of lines reaching the device, in 2021, we designed and experimentally tested this idea, combining the X, Y, and Z lines into a single line. So that we have 2 separate fridge lines that are combined with a diplexer, and then we have a single XYZ line reaching the qubit. So the qubit is built on this substrate. The XYZ line is on the cup. And here you can see the transmission coefficient of a diplexer. We have a low pass filter for the Z line and a band pass filter for the XY line with an extra echo source filter on the output. So this is an actual image of a qubit that was used for this experiment and the XYZ line on the top. We measured the qubit frequency as a function of flux, and we also ran single qubit gates, and we measured randomized benchmarking. We obtained good results. And now basically almost all of our devices employ XYZ lines. The last slide is about the interchip coupling. So if we want to scale quantum computers to hundreds of qubits, we also need to find a way to connect multiple chips together. So last year, we published this paper showing a 2-qubit gate between qubits built on 2 separate chips that were connected with a capacity coupling on the cup. And this result can be found in this paper. Yeah, with this slide, I would like to conclude my presentation. So if there are like any questions, I would be happy to answer.
Oh, sorry. Okay, now you could hear me. Thank you so much, Riccardo. That was an excellent talk. I guess we could, so we have both a virtual and also an in-person audience. Let's start with the in-person audience. One question. Yeah, just, what are they?
There's one question. when we have two input clusters, we have one geometry where higher qubit frequency to the tunable cluster is zero coupling, and one where one is zero coupling between the two transform qubits. So can we compare and contrast between the two?
Yeah, so you have two tunable couplers with two different geometries. And sorry, you're right. So in one case you have zero coupling, and then another case you have like a non-zero coupling. Can you, or
So let me go back.
the
So this
frequencies?
is-
you said. Yeah. Oh, yeah. Okay. But yeah. So both have zero coupling, but the frequency shifts are different. Can you compare? Well, I guess he's asking like, how do you map that change in frequency to the geometry?
Okay, so if I understand the question correctly, the question is about why like these two geometries achieve a G equal to zero condition. In one case, when the tunable coupler frequency is below the QB frequency, and in the other case, when the QB frequency, the tunable coupler frequency is above the QB frequency. So in these plots, the QB frequencies are indicated by these black lines. And the answer would be to really look at the capacitance network and derive like the Hamiltonian based on the capacitance network. And you will notice that when this capacitor between node 2 and node 3 is very big, and also the one between 4 and 5 is very big compared to the capacitances C35, C24, then you are going to achieve the G equal to zero condition when the tunable coupler frequency is below the QB frequencies. And instead, in this capacitance network, C35 is much bigger than C45. And in that case, we are going to achieve a zero coupling condition when the tunable coupler frequency is above the QB frequencies. So I don't think there is like a simple and intuitive way to see these. The calculations are shown like in the appendix of this paper. They're really detailed, and there you can see why this effect takes place. Yeah.
Okay. He has so the follow-up question is which geometry is better?
Okay, so this is a good question. So I don't know like if there is like a precise answer to this question, because when you build these devices, you need to think about the frequency allocation. So let's say that you have a qubits of 4 gigahertz, the tunable coupler of 5, then you need to decide where to place the resonators. For example, you can place the resonators at 6, 7 gigahertz. So it depends on the frequency allocation. So if you allocate like a specific frequency to the resonators, then you need to decide what to do with the other with the other QB frequencies. So for example, one problem that could happen is that if a tunable coupler frequency is above the QB frequencies, something that we notice is that sometimes the tunable coupler frequency overlaps with the resonator frequency, and so that could be problematic. However, this problem can be solved with like a fabrication technique that is very precise, so that the Joyson the resistance of a Joyson junction is very accurate, and the QB frequency is exactly is very close to the target value. So I don't think there is like an answer. Look, this geometry is much better than the other. We achieved really good fidelities to QB fidelities with both geometries. So I would say that the answer is it depends on the frequency allocation. It really depends which band frequency you want to assign to the resonators and which band frequency you want to assign to the qubits, which also ultimately depends on your room temperature electronics.
Are there any other questions? Yeah, we have one other. Hmm. Yeah, so the question is like within the superconductor, when you break up, well, yeah, it like occasionally like you would have fluctuations in the number of Cooper pairs from Cooper pair breaking. That's a noise source. How does that, your question was like, how does that affect the coherence or fidelity?
Yeah, so when we have a quasi-particles event, so basically, let me go back to this slide. So it might happen that, for example, a cosmic ray goes against the device and then breaks, it creates like some phonons, and these phonons break some Cooper pairs. And then we have like a quasi-particle moving from one side to the other side of the junction. And that is has an impact on the coherence of the device. And then also if the line does not have a sufficient number of echo filters, that could also be problematic. So usually when particle events happen, what you see is that the measurement of T1 shows like a double exponential decay. This there was a nice paper from the MIT group a few years ago about this phenomenon. And yeah, so that is a problem. So one way to solve this problem, so to mitigate like quasi-particle events, so the problem of like breaking the Cooper pairs is by introducing like echo filters on the lines, making sure that the device is like shielded from sources of noise. So there were also some papers showing that if are like objects that are decaying, so they're radioactive, close to the fridge, that could be a problem for the coherence of the qubits. So it all boils down to the packaging and how the device is assembled.
Is there anything else? Any online questions?
Yeah, I had a question.
Yeah, go for it. Just say it. Yeah.
How does Rigetti or have you ever explored or investigated phonons as a use for as an alternative for photons for sort of the RF control that you do?
No, we have not investigated that. So I would like to say that to run a single qubit gates, you just need to apply an electrical pulse. That's incredibly easy. And then for 2 qubit gates that are like the most challenging ones, again, if you go for the cross resonance gate, you just need to apply electrical pulses. If you go for like a tunable coupler scheme, then you would need flux pulses. We have not explored coupling between the superconducting qubit and phonons. I guess maybe you might need like piezoelectric somewhere, but it's also known in the community that when the substrate is a piezoelectric, then that might reduce the coherence time of a qubit. So if you introduce piezoelectric materials in your device, you need to be careful where you place them. Yeah.
So just to add to that, like phonons generally are like, because you have all of these like inelastic processes, and the fact that they're just like, you can't really control the phonon modes that you send, it leads to a lot of decoherence.
Thank you.
Are there any other questions? I have one question about how you do your benchmarking. So like what you showed was just for 2 qubit, like single 2 qubit gate. And you're reporting a fidelity there. What if you, I mean, what happens when you scale to many qubits? Does Rigetti use cross entropy benchmarking, or does it? What is their like scalable benchmarking technique?
Yeah, so cross-entropy benchmarking is quite interesting, and we're like looking into that. And we're also looking into quantum volume. So yeah, so these are like the benchmarking techniques that we are like considering as well. So because I think it's important to have like across the community like similar benchmarking techniques so that one can really test like the performance of a device and compare like the performance of different devices from different companies. So yes, we are both looking into cross-endonym benchmarking and quantum volume.
Are there any final questions? Yeah, there's one question. Slide 53. He's asking if the pulse amplitude and the 3D plot you have is that like the the actual pulse amplitude or the flux amplitude?
Yeah, so the pulse amplitude that I'm writing here is basically the flux pulse amplitude, so phi dc, and is expressed in terms of phi knots. So yeah, so this is like the flux pulse amplitude. I should have written flux here. And this pulse time is the flux pulse time. So the duration of a flux pulse. So this is T, this is T, and this is phi dc.
Okay. Okay, great. Yeah, I guess there's no more questions or comments. Thank you so much again. It was an honor to have you.
Thank you.
And I guess just some final words about QEGA. So this, as I mentioned, is the last seminar for the summer. We'll likely be picking up on the seminar series in the spring and be starting up other outreach and networking efforts this coming fall. So stay tuned in the email for all of those upcoming events. Great. Thank you so much.
Thank you.
All right. Bye.